So I'm just going to share my screen now. Okay, so hopefully that's showing up as an actual presentation. Great. Yes, so yeah, just to briefly start, as Helen just said, I'm Jade. I'm a partner engineer for games at Facebook. Today I'm going to be talking about arrays, linked lists, and hash tables. So just to give you a brief overview of the sort of structure. So for each of these three data structures, I'm just going to sort of do an examination of what the data structure is. So there might be a brief sort of what's the word, revision of some previous talks. I'll then sort of go into an examination of a typical implementation, sort of for some of these and various options, operations, sort of discuss the big O and explanations for those. Then have a quick overview of the strengths and weaknesses of various structures. And then finally, once I finished, I just realized that last breakpoint is bullet point is actually in the wrong, it should be on its indented back of it. Yeah, when the talk's finished, you can sort of break out into various groups and just work on a couple of sort of problems. So I'm going to get started with arrays. So yeah, what is an array? So in its most basic variation, it's a block of contiguous memory. So it preserves the order of elements as they are placed in the array. And as I said, it's kind of like in its basic, most fundamental state, it's immutable. That being said, there are variations that add extra functionality, such as, sort of allowing insertions or resizing and so on. Okay, so how would an array be built? So behind the scenes, when you create an array, what would happen is the block of memory is going to be allocated, and the amount of memory that's allocated will be the number of elements, that is to say the size or length of the array, multiplied by the size of each element. So for example, if you had an array with 100 integers, and assuming it was a 4-byte integer, it would allocate 100 times 4 bytes, which is 400 bytes.
Sorry for interrupting. I don't think you changed the slide. It's
oh,
the first one.
Is it not showing how array how part 1?
It shows what point 1.
Oh dear. Okay, sorry. This is, I think we had this issue the other day.
Yeah.
Okay, bear with me. I'm going to stop sharing and then reshare, and hopefully it will kick into action. Okay, hopefully that's updated now.
Now it's black.
All right, give it, I guess, maybe a moment to. No, brilliant. Third time lucky? Oh my gosh. Cool. And I've unmuted myself, so right. Yes. Okay. Just get back into the right mindset. Yes, so arrays. So assuming we want to allocate a block of memory, So that memory will be determined by the number of elements times the size of the elements. So as an example, we have 100 integers of 4 bytes. We would allocate 100 times 4, which is 400 bytes. Sort of more visual way of showing this. Consider a chunk of memory. So we can just see here, there's some existing assigned memory. We've given the code, my array is 4539. In the background, the memory for this array would be assigned as a single contiguous block, which would give us the layout that we can see in this little diagram. So things to keep in mind. It's also possible that maybe like the memory will be zeroed out as part of the allocation. It depends on the implementation under the hood. Maybe if we instantiate a piece of we instantiate an array, but we don't sort of provide any elements, we just sort of reserve that memory. Some implementations might have overhead depending on any additional operations that they may offer, such as maybe like null termination or things like that. And some might sort of preemptively assign extra memory to sort of support resizing, but we'll sort of look into a sort of dynamic array shortly. So yeah, a reference will be held to the start of the array in memory. And then that gives us sort of direct access to each individual element for read and write via the use of sort of subscripts. I'm hoping at this point that the slide has updated. Somebody wave at the screen if it's not updated to how part 2.
It's not, it's how part 1.
Oh my goodness. I bet Steve Jobs is laughing at me from wherever he is this now. Right. Yeah. Samira, did you manage to get those slides?
Very much for helping.
No worries.
Yes. So, okay. So, what I need to see now, right? Yes. So the reference is held to the start of the array. And we then have direct access to each element for read-write with the use of subscripts. So that is array, and then within the subscript, the square brackets index. And what we do is we determine, we know what piece of memory to access by taking the address of the start of the array, and then we add the index multiplied by the element size. And then so there's just a couple of brief, unfortunately I can't, oh maybe I can annotate, right, yeah. So we can see here in the example on the left, so we've got my array 453917. So number equals my array 3. So this is just to access the value at that element. So we know that my array starts, well, wherever my array starts, and we want the element at index 3. So we would multiply by 3 times the size of the element, which would give us the value here, which was 9, and then we print out the number 9. In this example, we've declared an array with, say, 3 strings. Now, just in case, or just to sort of avoid any kind of confusion, like obviously strings can vary in length. So what this might actually look like, even though we define this, you know, by putting the strings implicitly, or explicitly, I should say, in the declaration, behind the scenes, most likely we'd have something like, so we'd have a block of memory, oops, and we'd have like a reference that points to the string elsewhere. Yeah. And so in this case, what we're doing is we're getting instead of actually reading, we're actually assigning the value unicorn to the element at index 2. And so, whereas it would originally say car, what we're doing is we're assigning unicorn, so it would then have a reference to the string. And obviously, writing with letters with a mouse isn't so easy. But then when we print that out, as you'd see, we'd have cat, dog, unicorn. Cool. Thanks. So next slide, please, Samira. Okay, so yeah, so this is a sort of a worked example, I think, of that. So on creation, as I've previously said, the variable to the array knows whereabouts it starts in memory. So if you click again, yeah, so here we can see this diagram. My array points to the start. And then if you click again, and yeah, and given the fact that we know where the start of the array in memory is, and we know that memory is contiguous, what we can do is, yeah, so what we're doing for this example, say each element is 4 bytes. If my array starts at an address of 1,000, I've just used a random number here. I'm not going to bother with hex addresses and so on. Yep, if you could go on to the next bit. So this example here shows my array starts at the address 1,000. Each element is 4 bytes in size, and we want to target the 7th index. Next, and again. And so, yeah, what we do is we multiply, essentially what we're doing is we're multiplying the size of the element 7 times to get the address of that particular element. So you might have to click a few, like, so if you click Samira, and again, yeah. So you can see here what we're doing is we're essentially doing 1,000 plus 7 times 4, which is 1,028. Okay. Yes, so reasons why to use an array. So the access for read-write is constant. It's otherwise known as O1 time complexity, which if we have a known number of elements with lots of reads or writes or etc., it's great because we know we've got that instant access or to that data. It's a simplistic implementation, which means we can sort of use it in many different other data structures. And of course, there's sort of minimal, if any, overhead or wasted data, again, because it's such a simplistic structure. It preserves the order, which if we want to do things like sort data, or, where obviously the order is important, this is almost like a go-to. However, the implicit immutability of a simple array does, as I've said, prevent sort of resizing and inserting, with, just kind of like straight off the bat. That being said, it can we can evolve the simple array into something that's referred to or known as a dynamic array. Next slide, please. Oh, sorry, I've just seen a question. So 4 bytes to Lorna L, 4 bytes is the size. Oops, it was just an example. So maybe sort of using 4 bytes in like a 32-bit system for an. It was just the example. There's nothing magical about it. Sorry. Okay. So yes. So dynamic arrays. Yes. So with this additional functionality, it allows us to make our arrays mutable. That is to say, we can add and remove or insert Okay, sorry, and sorry, just briefly, so the question I answered, the question that came in was, could you explain how you arrived at 4 bytes for those previous examples? Yeah. Sorry, yes, so the mutable array, it gives us the ability to add, remove, and insert. Like,
What's happening?
I think there's an issue with the slide controls. Could you go to the next slide, please?
Yeah, sorry, I was trying to find what slide was relevant.
So we want to be on dynamic array, which is what part 2.
So that's right.
Yes, thanks. Yeah.
Okay, sorry.
No worries. Yes, okay, so we retain the contiguous layout in memory, which is great because that means we can still have our direct access, so it gives us a constant time complexity for accessing, reading and writing. However, there is a potential high cost of resizing. That being said, we can sort of mitigate that with various techniques by resizing with larger factors than is necessary. So for example, if we just want to add a single element, we can still sort of resize by maybe a 1.5 or double the size. And so what that does is it means that the number of resizes we're going to have to do over time or the frequency of resizing would get less and less, as opposed to if we do it one at a time, because that could be very costly. Next slide, please. Cool. So thank you. Yeah, so just a quick example of how we'd do a resize. In an ideal situation, if there's memory available after our existing array, we can just simply allocate the extra memory at the end. So yeah, so if we called the code petsArray.append and we wanted to add dragon to our pets array, what we would do is we would just say, for example, we'd double the size of our array, and then we'd be able to add dragon. And now pets array is essentially the full 8 elements, as opposed to it used to be 4. Even also, yeah. Just a quick side note to the previous. Even though it's like got the physical 8 elements of memory allocated, if you were to call size, most implementations would still give you the sort of logical size, which is just the 5 elements. Okay, unfortunately, there are cases where we might need to allocate a new larger block of memory than we have available to us. And in that case, what we'd have to do is create this chunk of memory somewhere else in memory, and then just copy each element across. If you could click, please. Yeah, so we've got pets array here, and we've been adding elements to it. But in the meantime, if you click again, something else has been allocated. So now if we want to add dragon, we can't easily do that. So what we have to do in some completely other part of memory, we'd allocate a chunk that's going to accommodate all of our elements. And then we'd copy each one across, and then finally add the newly added entrance. And then we'd free up the previous memory. If you click. And then finally, and so because we've had to do all of that work, time complexity of that operation would be seen as ON. So it's linear, and so the larger the array, the more work has to be done. And that's why we'd like to ideally sort of reduce the number of times that we have to do that. Okay, next slide, please. So if we want to insert at an index, what we would need to do is we'd need to essentially split, say split is probably the wrong word, we need to sort of consider the parts of the array. So we want to go from the start of the array to the point at which we want to insert our item element to. And we then want to have the items from the point that we want to insert to the end of the array. We then need to allocate memory to accommodate this. Then copy all of the elements from everything up until where we're inserting. Place the element that we've, the item that we've added to the array, inserted at the insertion point. And then we'd copy the rest of the pre-existing elements from the old array to the new one. And again, this is linear ON time complexity because you're having to go through the whole array. Next slide, please. And so just like now, a kind of a worked example of that. So we can see here we've got a block of memory, dog, cat, unicorn, rock. And if you click, so we want to insert index to the dragon. So what we do is we allocate this new block of memory, which will accommodate everything and obviously has a bit of extra allocated memory for future operations. We then copy dog, cat. We then insert dragon, and then we finish copying the rest of the array to the new position. And then finally, we do our cleanup. So we point the variable to the new array and free up the previous memory. And yeah, so just a quick chunk of code. If we were to call that and then print out pets, that's what we would see. And next slide, please. So before I go on with linked lists, is it worth pausing for any questions, or should I just plow on? I will continue on. Cool. Right, so a linked list consists of nodes that have the object themselves and a link or a reference to the next node. So in just a quick example of that. So here we've got a node with dog, and there you can see there's an element for next. Then maybe we add something to the linked list. And here we've added cat. So then the next from the dog node would then point to the cat node. Yep. And then say we want to add a rock. So we'd create the rock node, and then the next element from cat node would point to the rock node. So a couple of things to see here. You can see there that the rock node wasn't allocated right next to the cat. So of linked lists, they are not contiguous in memory. So they can be anywhere. And also you can see I've used a little cross symbol just to kind of symbolize that the linked list has a null terminate, to sort of signify that that's the end of the linked list. If you click, please. It's also possible that nodes would have a link to their previous node. This would be seen as a doubly linked list. So we can see here our cat node, previous is null, and for dog, next is null. So it's like the start and the end of the linked list. And then next of cat would point to dog, and previous of dog would point to cat. And click in. Thank you. And then next slide, please. So yeah, as I previously mentioned, the memory is allocated as it's needed, which is great. It means we can grow and shrink as we go along. We don't need to rebuild the entire structure, which is something we see with the immutability of arrays. And the order is preserved. again, handy for things like queues or stacks. And so the fact that nodes are not contiguous in memory means if you click in, we forfeit the random / direct access because we don't know where the next, or rather, we can't mathematically calculate where the next node is in memory. We have to traverse the entire structure to find a specific node that we want. So yeah, just a bit of code snippet here. So we have a node class, very simple one that has the data and the next. And then here we have our linked list. So we create our linked list with some data, optional data, and we create an instance of the node for that. And that is the head of the linked list. When we have add, what we would do is we would start. So first of all, we'd assign the node or the head node, and we would traverse through our entire linked list until we came to the end. The end would be signified as the node whose next property has nothing assigned to it. And then what we do is we would assign in the next property of that node, that is the tail of the linked list, the node that we're creating now for that newly added data. And then I've just added also a quick output function, which would iterate through the linked list, building up a string to output the contents at the end. So if you click once more. Thanks. So if we created a linked list with cat, then we added a dog and then a dragon, and then we output that by calling the output function. The output that would be seen is cat, dog, dragon. So this is a worked example of adding a node to the end of the linked list. So yeah, we've got our pets list here. We point to cat, dog, rock. The property of next in the rock node is null. So if you could click, please. Yeah. So we start at the beginning and we traverse until we find the node that has none or null in its next property. So what we do is we start at cat. If you could click, yep. The next property of cat points to dog. The next property of dog points to rock. And then obviously we've established that rock has none in its next property. So we can create the new node. And if you click, yep. And now we can point from the next property of the rock node to the dragon node that was newly created. And one more click, please. Yeah, and so this addition is seen as linear complexity, again, ON, because we've had to traverse the entire data structure. And again, as that grows, so too will the amount of work necessary to add to the linked list. One thing that's worth noting, if we had a certain implementation of a linked list that maybe maintained a point to the tail of the linked list, then the addition would be seen as constant because we've got an automatic jump to where we need to add the data. So we would be able to mitigate the linear search there. So this is now a worked example of inserting. So yeah, so what we can see here is we've got, from our previous example, cat, dog, rock, dragon. But we want to add a unicorn because let's face it, unicorns are probably the best pets. Okay, so if you could click again, please. Yeah, so here we go. We've created, so we've gone through our linked list and we've to the point that we want to insert, and we've created our unicorn node. Now what we do is we take the so we keep a reference to the rock node, which is the current next for the dog node, And then what we do is we replace dog.next to point to unicorn, and unicorn.next would point to rock. So if you click, so the insert operation itself would often be listed as constant because it's like a discrete operation. If you click again, please. Yeah, so the insert itself is like constant access, just creating the node, pointing and fixing up the pointers. And one thing that sort of confused me before when I was like used to sort of look into this, I was like, well, I'm still having to traverse through the whole linked list. Like, why is that? And yeah, so technically the seek would be considered ON, but because the insert itself is a discrete operation, that's why you might often see it written as constant time complexity. And one more click, please. And yeah, so in the same way, this is a similar process for sort of removing. You go through, you find the node that you want to remove, and then you find its next node, and then you just kind of hook up the previous one to the node that's being removed's next one, and it's and then free up the memory, and then you're good to go. So yeah, linked lists are useful for things such as queues and stacks. And yeah, if you, as I mentioned previously, if you maintain pointers to the first and last nodes, then you can sort of reduce some of the complexity for some of these options, like adding at the start and the end. So things where there's like lots of push and pop operations would give you minimal overhead. Things like this would be stacks and queues. So from a previous talk, I was mentioned like for queues, if you have like some kind of an operation processing thread that you sort of in-queue tasks to, and it just kind of takes the task from the front of the queue. Examples of stacks might be persisting state of maybe a scene graph or something. If you want to apply different matrix operations and so on, you know, sort of if you're doing some kind of graphical simulation or what have you. And obviously the lack of needing to sort of be resizing and all of the overhead that you might see with arrays makes this linked list quite well suited for that. Obviously, if it's like a fixed queue length, then you know an array is not too bad. But if you're, you know, if it's very dynamic and you don't know what you're going to be dealing with, that's when the linked list is handy. And yes, linked lists can also find use as part of the construction of a hash table, which is something that we're going to look at next. Oh, sorry, I just see there's a another question. How does a Python list work? Is it an array or linked list or something else? Okay, so Python's not my first language, so please correct me if I'm wrong here. My understanding is the Python array is pretty much written, built on top of a linked list in the background. I think that's what it said in the documentation that I was reading the other day. I apologize if I'm wrong, and I would definitely encourage somebody who knows better to speak up and correct me. But I think that's what the case is, because the definition, the way you sort of define an array and a linked list with Python, I think are very similar. Welcome. Yeah, I'm guessing that nobody said otherwise means that hopefully right. There we go. So Helen's just said, cool. Okay, so Helen said it might be a dynamic array under the hood, and Maria's shared a link to something else. So hopefully one of those sources will be able to answer your question. And if what I've said is wrong, I apologize. And I'm definitely going to read up on that after this because I now want to know the answer as well. Okay, so hash tables. So they map pairs of keys to their values. Essentially, you would have an array of buckets in which the values are stored. And there's a hashing process. So the key for the value is applied, goes through a hashing function, and we take the pre-hash, and then from that we would convert it into the index of the bucket to use. One way to do this would be to just apply a modulus to the value of the key, the hashed key, to define the index of the bucket to place that value into. If you could click, please. So yeah, the ideal here is that we want to have a one-to-one sort of mapping of one value per bucket, at most. But that's obviously not always possible. There's various reasons for this. And as a result, there are techniques to alleviate the collision hashes, hash collisions. And something that's quite important to know about sort of the standard hash table is without any kind of extra functionality in an implementation, in general, the order is not preserved. That being said, one of the big strengths of the hash table is we can take the amortized complexity for access, insert, add and remove can be taken as constant, which is obviously very beneficial if you're doing lots of these operations. Okay. So this is just a quick example of how we might insert a value into a hash table. So what we can see here is an array of buckets. And so maybe we want to map a pet to the name. So cool. Yeah, so here we've got key value. So the key is dog and value is spot. So what we would do is we generate a hash from the key. So like this hash function, it's a huge area of research on its own. It's definitely beyond the scope of this talk because there are so many factors to consider to make sure you get a good hash function, and you want to make sure you have sort of uniformity and so on, like for distribution amongst your buckets and so on. So for this example, I've just done a really simple function whereby I apply a numerical value based on the letter, and then I carry over the value. So if I apply values to the letters D, O, and G, or I would get the value 557. I'd then mod that by the bucket count, which for this example is 10. And then that gives me the value 7. So that would mean that spot would be placed into the bucket at index 7. And then we get. So then next slide, please. Yeah. So as I said, like the collision function, the hash function I just mentioned is really basic, and you would very quickly start to see collisions. And so that's why we need things like collision resolution. One such example of this is instead of storing the value directly in the bucket itself might point to a linked list. So in this example here, we can see we've already got an element in we've already got a fish called Bella at the start of the linked list stored in the 7th bucket, or the bucket at index 7. And then here we go, we're trying to add Spot the dog. And so we've gone through, we've got 7, which again is going to cause this collision. So what we do, if you click once, and then again, so essentially we add it to the end of the linked list in that bucket. You can also see in the example that as well as the value itself, we're also storing the key. So we're storing fish, Bella, dog, Spot. The reason for that is when we come to fetch the value, we also need to make sure that the value we're returning is the correct one based on the given key. So if you click again, please. And once more. And yeah, so in this case where we have got a linked list for a collision resolution, it does equate to a worst case of linear or ON time complexity, because again, we'd have to, with a really poor hashing function, we might find that we have every single element or every single value that's added to the hash table in the same bucket. And so obviously that would be very much a worst case, but it would take, potentially you'd have to enumerate through every single value in the data structure to find the correct one. Cool. So other collision resolution techniques do exist. One such is a field known as open addressing. There's actually various techniques for this, but essentially it involves finding an open slot when a given bucket is taken. So I think like one of the sort of go-to techniques here is just going straight for the next open bucket next to the one that you're trying to insert to. And if that next one is taken, you find the next one and keep on going until you find an empty bucket. This, of course, limits the number of entries to the number of buckets here. So the reason for that is, well, we're storing the values in the buckets again, and obviously we can't have more values than we have space assigned for the structure. And this is yet more reason that we want a hashing function that has like an even distribution, because what we want to do is we really want to avoid clustering. If you click please. Thanks. So the reason for that is if you have a hashing function that starts placing lots of elements in close proximity to each other, the clustering would sort of see us quite often having to keep probing bucket after bucket until we find an open space. Whereas if we have a more even distribution of our results from the hash function, even if there are collisions, it would mean there's not so much time spent probing the next bucket to get the solution, the free space. And a high load factor would make this quite difficult to avoid. And by high load factor, I will, if you could go to the next slide, please. Yeah, so the load factor refers to the number of entries divided by the number of buckets. And as I've just said, if with a higher load factor, you've got more chance of collisions and therefore you're going to have performance hits. Obviously, the reason for that is if you've got more elements in your hash table, yeah, there's just more chance of sort of two keys having a collision. Yeah, so something you might want to do to mitigate this is when your load factor exceeds a certain threshold, say, I don't know, maybe 0.5 as an example, you might want to resize the number of buckets in the hash table. What you then want to do is move all of the existing elements from the current hash table to the new one. And even this in itself, sort of rehashing, has various techniques. You know, I guess the sort of most simple one would be, okay, I've created a new hash table, so I'm going to take all of my existing values and place them into the new table. Another one would be, for every time I access the existing hash table, I might copy a few from the old one into the new one, and so on, until the old one is empty, and then we can just free it up. And again, if you have a good like factor that you apply when you resize the hash table, and you know, given so the amount you resize it by and the load factor at which you sort of initiate this, the work needed to do that can be amortized to be sort of constant. So again, it's like you just kind of want to reduce the frequency at which you have to do these resizes. Okay, so why use a hash table? Yeah, so it's constant time complexity for lots of the operations: add, remove, insert, and read. With large data sets, or indeed lots and lots of read writes and accesses, you know, this is where those performance gains become really quite apparent. But of course, if you're working with something that has a poor hash function, then you could start to see having linear performance, which is obviously, again, with larger data sets, is going to really sort of start to notice and affect performance. There's other different kinds of hash tables, like, so for example, you could use a set, which sort of guarantees or forces, I should say, a single instance of each key. And you know, they'll often be seen to give you sort of mathematical set functionality, like unions, intersects, and so on. It's a good way to remove duplicates. So, you know, if you ever happen to get like an interview question, it's like, oh, how would you remove these duplicates? You know, you could consider using a set. And yes, with hash tables also, caching is great because you've got fast access to the data that's cached. And yeah, so this caching is used not just in like for our algorithmic problems, but also like real world stuff as well, which is always good if stuff has real world uses. So yeah, I think that's the end. Thank you for your time. Apologies for the interestingly approached to slides. But yeah, I guess at this point I hand back to Helen. And yeah.
Thank you very much.